Thank you. Good afternoon. Actually, this was exactly the introduction I want to give. We have heard a lot about the deep sea, and now I want to take you in the high Alps. I will report on an exploration study I conducted in cooperation with the chair for resource mineralogy and Professor Wright at the Montagne University Leoben and Wolfram Bergbahn-Hüttner AG, which is the mining company who mines the Felbertal ore body in Austria. And I want to discuss the question if more yet to be found in the Alps based on our recent findings. So basically, Wolfram Bergbahn-Hüttner AG is the miner of the probably, from my perspective, the largest tungsten deposit in Europe. It's located in Salzburg in Austria. It is a granite-bound magmatic hydrothermal deposit that is sitting in Cambrian island arc amphibolites. It was found actually during a student stream sediment sampling campaign in 1967, and the eastern ore field, and it's separated in two parts, in the eastern ore zone and the western ore zone. The eastern ore zone is outcropping, and therefore the students from Munich quickly found scheelite traces, and then they found the deposit. Exploration and work there was heavily impaired by the very tough, steep mountainous terrain and unpredictable weather conditions. I will show a picture in a second. And the exploration needed 8 years to delineate the eastern ore zone, and then they quickly realized, okay guys, there's also a western ore zone, and the western ore zone is currently mined underground and is actually by far the largest resource in this area. Regarding the open pit, I want to say that the harsh climatic conditions forced seasonal open pit mining. And how this actually looked is this. So this is a picture from beginning of September during the field work. Yeah, it's in 2,500 meters altitude, and actually it looked exactly the same on the 23rd of August when the first 30 centimeter fresh snow fell. But this is the better picture, so I show this one. We see the location is called Messelingscharte, and it's located exactly here. It's like a small pass. And at Messelingscharte, we find 4 types of mineralization in a spatially confined area of about 250 times 250 meters. The most important mineralization type are Scheelite-rich calc-silicate rocks, which is actually a picture from here. I just want to stress here that this outcrop has visited by thousands of people because the hiking track exactly runs here. And this rock contains up to 7% tungsten. Okay, then there's also in the area some discordant Scheelite quartz veins and also scheelite amphibolite molybdenite layers and joint and scheelite and joints, which is pretty obvious in the Alps. So just a few words to the location. So the location, Felbertal is located in a town window, which is the largest of 3 tectonic windows in the Eastern Alps, exposing metamorphosed European crust. And Messelingscharte is about 6 kilometers south of the large deposit, and you can go there by foot if you are a little bit in training. And it's located on the western margin of the big Granatspitz-Gneiss Pluton. This mineralization I want to show is hosted by early Paleozoic basal amphibolite, which is actually not the same host rock as the deposit, but they're very closely related. And moreover, the Felbertal Augen gneiss is very close by, and this specialized I-type granite gneiss plays a huge role in the formation of the Felbertal deposit. So let's take a look. So of course, every exploration starts with field work. That took about 3 months, and then I did bulk rock geochemistry and quantitative XRD, of course, thin section, all the kind of process, and we see here the summarized results. So the calc-silicate rock contains 50% clinozoisite, 15% plagioclase, 6 molar percent scheelite, and a lot of quartz. The bulk rock geochemistry is characterized by very high tungsten content. So on average, the whole average from all samples is 4.5% WO3. Those values were measured with a specially calibrated XIF from the mine, so they're reliable. Then we also find tin, on average about 1,000 ppm, as well as quite high beryllium values. I want to stress here that sampling of those mineralized rocks, of course, were accompanied by a regional sampling program. So I can say you that the amphibolite host rock is completely tungsten, tin, and beryllium free. So that's a pretty huge anomaly. And well, what's striking here is we find 1,000 ppm tin, but there is absolutely no cassiterite. Literally, there is no cassiterite. And I will address this issue, of course, in a second. Let's take a look at some trace element geochemistry to investigate the genesis of this exotic rock. We see on the left-hand side some, let's say, immobile elements, at least they're considered to be immobile. The gray background is the amphibolite host rock, and those are the reliable samples I took. We see that that mineralized calc-silicate rocks inherited some unique features that are also present in the amphibolite host rock. Especially, I want to stress here the quite high and strongly scattering thorium values that are interpreted as varying degrees of crustal contamination of this basal amphibolite. Moreover, we see quite weird depletion of hafnium, zirconium, and titanium, where actually neither I nor my professor nor anybody I talked to had a clue what this is on about. Moreover, we see enrichment of strontium, which can be explained by the addition of calcium because it's a calc-silicate rock. Yeah. So regarding the rare earth element pattern, we see actually a flat shape, and we see here a depletion of light rare earth elements compared to the amphibolite host rock, which indicated during the metasomatism, during formation of those calc-silicate rocks, light rare earth elements were mobile. As well, we have a huge europium anomaly, and this is explained by incorporation of europium-2+ into calcium-bearing minerals like the clinozoisite and the feldspar. So let's take a look at two major minerals that hopefully provide some insight into the genesis of this rock. Of course, scheelite is the primary target, and therefore this is a cathodoluminescence picture of scheelite that I modified here a little bit. Basically, we see three generations of scheelite. So scheelite is polyphase, similar to the deposit. The generation 1 is molybdenum bearing. It has a yellow luminescence color, and it's macroscopically visible. I have here a small hand specimen, so all geologists can please take a look at it. Sure. Yeah, let's go on. We see here fine oscillatory growth zoning, like here, which is also very characteristic in the close-by Felbertal deposit. And then we see generation 1, which is interpreted as a metamorphic recrystallization. Why? Why it is not an additional tungsten input later on? Because we see some, for example, here, relictic oscillatory growth zoning, and furthermore, we find molybdenite crystals, because this generation 2 is molybdenum poor, and therefore the molybdenum has to go somewhere, and the molybdenum goes into molybdenite. Generation 3 is basically only metamorphic overprint in some brittle cracks and so on. And now if we compare this to the deposit, of course, the aim of this investigation was also to trying to link this high-grade tungsten rock somehow to the deposit, because then we could draw more broad-scale conclusion. So the first generation is interpreted as a Varischian scheelite, very similar to the deposit. This has important implications because in the Eastern Alps, there's basically only Varischian scheelite located in the deposit, in the Felbertal deposit. So if this is really true, as interpreted, then this could be the second described occurrence of Varischian scheelite in the Alps. The second generation, the first metamorphic rim, is interpreted as a Varischian metamorphic recrystallization, similar to the stage 3 scheelite in the Felbertal deposit. And the generation 3 looks very young. It feels brittle cracks and so on. Therefore, it is interpreted as an alpine metamorphic recrystallization. This has very important implications because those metamorphic zonation really indicates that this is not a local alpine accumulation of scheelite like it is very often present in some joints or so. It seems that this is properly old and it's Varischian. Then, a second mineral that I want to talk briefly is the clinozoisite. I mentioned briefly that on average there are 1,000 ppm of tin and there is no cassiterite. So of course, yeah, the investigation started, okay, where's the tin, guys? And the tin is actually hosted in a clinozoisite, nearly exclusively. There's also some titanite in this rock, but it's not much. Basically, it's 1% titanite or so. So basically, all those 1,000 ppm of tin are hosted in clinozoisite, and that's very rare. Also, clinozoisite shows 2 generations. I put here a backscatter electron picture with some electron microprobe measurements, and we see here very high concentration of tin, 3%, 2.5%, 2.3% SNO2, and those values are actually among the highest recorded values for tin in clinozoisite ever. Staniferous clinozoisite is very rare. There are only 3 occurrences in the world that were properly described, and actually 2 are in Cornwall. And all of those 3 occurrences are directly associated with magmatic hydrothermal activity. Also, I want to show the next picture, which shows how the substitution of tin and titanium works in clinozoisite, because that's actually not obvious, because clinozoisite has has mostly a position here for 3+ aluminum and a little bit of iron, and tin and titanium are 4+. So actually you need a proper substitution to get the charge right, and you can calculate with mass and charge balance from electron microprobe data how much Fe2+ is in the clinozoisite, and here we see the results. The proposed substitution is pretty much valid, and we see that actually the measurements are very close to the ideal substitution line. And this is also the largest data set for tin-bearing clinozoisite that is currently available. So, sorry, 2 minutes here, perfect. This is basically a summary. That summarizes actually everything. We have here the scheelite zonation. We have a primary molybdenum-rich magmatic hydrothermal scheelite that is recrystallized 2 times, as well as a primary clinozoisite that has a very diffuse and chaotic internal zonation based on tin and titanium that also got recrystallized and thereby changing to this characteristic shape that is indicated here. So a quick comparison. I mentioned that those staniferous clinozoisite is very rare, and those are the 2 locations in Cornwall. So in Cornwall, there is actually not staniferous clinozoisite, but staniferous epidote, and both occur in skarns. We see here, for example, Alderton and Jackson described skarn veins in hornfelses, or von Marke de Lumen described a massive retrograde skarn with also quite high values of tin. And then actually, I can't answer the question if this rock here is really a magmatic skarn. I literally don't know. We see here a list of pros and cons. So what are pros? We see a calc-silicate mineralogy. We see tin-bearing clinozoisite, plagioclase, tin-bearing titanite, scheelite, and amphibolite. We see an enrichment in granitophile elements like tin, tungsten, beryllium, bismuth, uranium, and copper. The regional geological context would fit to formation of a skarn, because we have the specialized granites in the area, and we have the deposit in the area where it's proven that there is a magmatic hydrothermal system present. And the polymetamorphic overprint indicates that this is not a kind unique alpine accumulation. No, it seems to be that proper Varishian mineralization event. The con side is actually pretty heavy, because in this rock there is absolutely no garnet, no pyroxene, there are no other typical calc-silicate minerals, no Vesuvian, no nothing. Basically only clinozoisite, what I showed you. Also the host rock is pretty unusual with an amphibolite, and the small and irregular size makes it currently not suitable for mining, of course. But what is for me important is that if the conclusion is right, that this is a magmatic hydrothermal skarn, this could be the first outcrop and a first indication of a larger magmatic hydrothermal system that has the potential to create a mineable ore body similar to the Felbertal Scheelite deposit. I want to thank now my academic advisor and of course the company to finance this project, and I still want to ask the question if more yet to be found, and I want to cite here the ex-CEO from Eurasian Minerals. I talked to him at a conference in Levy, and he told me that he thinks that the Alps are underexplored other modern standards. Thank you.
Thank you, Alexander. Great talk. We got a bit of time for some questions from the audience.
Please.
Catherine.
I feel this might be a silly question, but how close is the nearest Veruscan granite? Is there Veruscan granite
the
nearby?
Yes. The Felbertal Augeneis is this highly specialized I-type granite. It's about 300 meters away. You can walk there if you're a little bit tough in 15 minutes, and it's also actually in line of sight.
Yeah, okay.
Anyone else?
Yeah. So this is the Großvenediger, the second largest glacier in Austria, if you're interested. Yeah.